The birth of a black hole, the enigmatic objects that warp the fabric of space-time, have fascinated scientists and stargazers alike for centuries. These regions of space where gravity is so strong that nothing, not even light, can escape, are born from the most extreme and cataclysmic events in the universe. The formation of a black hole begins with the collapse of a massive star, its fate sealed by the very forces that keep it burning. As stars burn through their nuclear fuel, they balance gravity with the outward pressure of nuclear reactions. But when a star runs out of fuel, this balance is disrupted, leading to an inevitable collapse. A stellar mass black hole forms when a massive star, typically at least 20 times the mass of our Sun, reaches the end of its life cycle. With no fuel left to support the outward pressure, the star can no longer resist its own gravity. The core collapses inward, compressing its mass into an infinitely small point called a singularity, where the gravitational pull becomes infinite and space-time itself curves to an extreme. This singularity is surrounded by a boundary known as the event horizon, the point beyond which nothing can escape, not even light. The birth of a stellar mass black hole marks the end of the star's life, but also the beginning of a new, bizarre phenomenon, an object that can consume everything in its path, warping space-time in ways that challenge our understanding of the universe. However, supermassive black holes, which are millions or even billions of times more massive than the Sun, present an even deeper mystery. These giants are found at the centers of most galaxies, including our own Milky Way. The precise mechanism behind their formation remains unclear, though several theories exist. One popular hypothesis suggests that supermassive black holes may form from the collapse of massive gas clouds in the early universe, or from the merging of smaller black holes over cosmic time. Alternatively, they could grow by accumulating gas and matter from their surroundings, gradually increasing in mass as they absorb stars and interstellar debris. Regardless of their origins, these supermassive behemoths play a crucial role in shaping the structure and evolution of galaxies. The event horizon is where the mystery of black holes deepens. Once something crosses this boundary, it is pulled inexorably toward the singularity. What happens to matter and energy inside the event horizon is a question that defies our current understanding of physics. According to general relativity, time and space behave in bizarre ways near a black hole. For an external observer, time appears to slow down as an object approaches the event horizon, making it seem as though the object is frozen in time. But for the object itself, time flows normally until it crosses the event horizon, where the rules of classical physics break down completely. Despite the known mechanisms behind the formation of stellar mass black holes, the exact processes that lead to the creation of supermassive black holes and the behaviors inside the event horizon remain a mystery. The deeper we probe the nature of black holes, the more we realize that they challenge the very limits of our scientific understanding. These cosmic monsters not only warp space and time, they also blur the lines between known physics and the unknown, revealing that the universe holds far more secrets than we can yet fathom. The point of no return, the event horizon, marks the boundary of a black hole. The point of no return where the gravitational pull becomes so strong that nothing, not even light, can escape. This boundary defines the edge of the black hole, and once crossed, an object is irrevocably pulled toward the black hole's singularity, the infinitely dense point at its core. The concept of the event horizon is central to our understanding of black holes, and it presents one of the most profound mysteries in physics. While we can observe the effects of black holes, the event horizon itself remains an elusive and enigmatic feature, seemingly both an end and a beginning. The event horizon is not a physical surface, but rather a mathematical boundary in space-time. As an object approaches the event horizon, the gravitational pull increases exponentially, warping space and time in ways that challenge our intuition. For an outside observer, an object falling toward a black hole appears to slow down as it gets closer to the event horizon, its image becoming increasingly redshifted, eventually fading away. This happens because, in the intense gravitational field near the black hole, light itself loses energy, stretching out into longer wavelengths until it becomes invisible. From the perspective of the object falling into the black hole, however, time and space remain normal, and the journey across the event horizon would seem uneventful at least until the object reaches the singularity. At the event horizon, space and time lose their usual meaning. According to general relativity, inside the event horizon, gravity is so powerful that it distorts the fabric of space-time to such an extent that the usual direction of time itself is reversed. What was once the forward direction of time becomes a path leading inexorably toward the singularity, the ultimate endpoint where all matter is crushed to infinite density. In this sense, the event horizon marks the point where time itself is no longer a guide for an object's trajectory. Once inside, everything is drawn toward the singularity, and all physical laws as we know them seem to break down. The most perplexing aspect of the event horizon is the question of what happens to the light and information that cross it. While we can infer much about black holes based on their observable effects like the powerful X-rays emitted by material being pulled toward the event horizon, what happens to the information contained in matter that falls in is a profound mystery. Hawking radiation, proposed by physicist Stephen Hawking, suggests that black holes can emit radiation and slowly lose mass over time, leading to their eventual evaporation. However, this theory also raises a critical issue: the information paradox. According to quantum mechanics, information cannot be destroyed. But if all matter that crosses the event horizon is swallowed by the singularity, it seems that information is lost forever. This paradox has led to some of the most profound debates in modern physics, as scientists struggle to reconcile the laws of quantum mechanics with the nature of black holes. Could it be that the information trapped inside a black hole is simply lost, erased from the universe forever? Or is there a way in which the information is preserved, hidden beyond the event horizon but still intact in some form? One possibility is that the information is encoded on the surface of the event horizon itself, a theory known as the holographic principle. This idea suggests that the three-dimensional information of an object can be stored on a two-dimensional surface, like a hologram. If this is true, then the event horizon might not be a complete barrier to information, but rather a place of transformation, where information is preserved but in a form we cannot yet fully understand. The mystery of the event horizon and the information it holds stretches to the very limits of human understanding. It is an area where the most fundamental laws of physics, general relativity, and quantum mechanics collide in an unresolvable tension. While general relativity predicts that information is lost forever inside a black hole, quantum mechanics insists that information must be preserved. The resolution of this paradox is one of the greatest unsolved problems in physics, and its answer could have profound implications for our understanding of the universe, the nature of reality, and the future of theoretical physics. Beyond the event horizon lies not just the singularity, but also an infinite mystery. The singularity itself is a point where the laws of physics break down completely. Here, gravity becomes infinite and matter is crushed to infinite density, rendering the equations of general relativity nonsensical. It is a place that defies our comprehension, a region where space, time, and matter no longer follow the rules we understand. And yet, it is central to the structure of black holes, the most enigmatic objects in the universe. Despite all our advances in astrophysics and cosmology, the event horizon remains a boundary we cannot cross, a concept that stretches the limits of our scientific imagination. In conclusion, the event horizon represents both the ultimate edge of the known universe and the threshold to an infinite mystery. While we can infer much about the behavior of black holes from the outside, what happens beyond the event horizon remains a fundamental unknown. The mystery of what lies within this boundary, whether it be the fate of light, information, or the very fabric of space-time itself, remains one of the most captivating challenges in the pursuit of knowledge. The event horizon is not just a point of no return, but a symbol of the limits of human understanding, pushing the boundaries of both physics and philosophy. What happens inside a black hole? Once something crosses the event horizon of a black hole, it is drawn inexorably toward the singularity, the heart of the black hole, where the laws of physics as we know them completely break down. While we have a solid understanding of how objects behave near the event horizon and can observe the effects of black holes on their surroundings, what happens inside a black hole remains one of the greatest mysteries in modern physics. The singularity, where gravity becomes infinitely strong and space-time is warped to its extreme, is a place where our current models of physics cease to be useful. At the core of the black hole lies the singularity, a point in space where the density of matter becomes infinite. Here, the gravitational pull is so strong that not even light can escape, and the fabric of space-time becomes infinitely curved. According to general relativity, as an object approaches the singularity, the effects of gravity become more pronounced, stretching matter and distorting time itself. In theory, all of the mass of the black hole is concentrated at this infinitesimally small point, creating an infinitely dense object. However, the equations that describe the singularity's behavior are mathematically singular. They break down when they reach this point, suggesting that our current understanding of gravity and spacetime is inadequate at such extreme scales. Essentially, the singularity is a failure in our understanding of physics. General relativity and quantum mechanics, two pillars of modern physics, do not agree on what happens inside a black hole. General relativity predicts infinite density at the singularity, while quantum mechanics suggests that on the smallest scales, the nature of space-time is more discrete and granular. These two theories are fundamentally incompatible in their description of the singularity, highlighting the need for a unified theory of quantum gravity. As matter approaches the singularity, it experiences spaghettification, a process where the immense tidal forces stretch and compress it due to the extreme differences in gravity between the top and bottom of an object. For example, an astronaut falling into a black hole would be pulled apart, their body elongated like a strand of spaghetti as the forces near the singularity tear it apart. This happens because the gravitational field near the singularity is so powerful that it creates differential forces strong enough to distort the shape of any object that falls in. One of the most perplexing questions about black holes is what happens to the information that falls into them. According to the principles of quantum mechanics, information cannot be destroyed, but general relativity suggests that once something crosses the event horizon, it is lost forever. This information paradox has puzzled scientists for decades. If information is lost inside the singularity, it would violate the fundamental tenet of quantum theory, which asserts that information must be preserved. However, if the information is somehow preserved within the black hole, it raises further questions about the nature of the singularity and how we can reconcile quantum mechanics with general relativity. Some theories suggest that information may be encoded on the event horizon itself, in a concept known as the holographic principle. This idea proposes that all the information about the matter that falls into the black hole is not lost, but instead is stored on the surface of the event horizon, similar to a hologram. If this is true, then the interior of a black hole may not be as mysterious as we think, and the information could eventually be retrievable, though the details of this theory remain speculative. Despite these theoretical frameworks, the true nature of what happens inside a black hole is still an open question. The singularity is a region where the known laws of physics break down, and where space and time become distorted in ways we cannot fully comprehend. As we continue to explore the nature of black hole, one of the most profound challenges remains: how do we reconcile general relativity and quantum mechanics? And how can we understand the interior of a black hole in a way that makes sense of both theories? Until we develop a unified theory of quantum gravity, the interior of a black hole will remain one of the most mysterious and unexplored frontiers of the universe. The wormhole hypothesis, the idea of wormholes, also known as Einstein-Rosen bridges, has captivated the imagination of scientists and science fiction enthusiasts alike. These theoretical structures in space-time are proposed shortcuts, allowing for instantaneous travel between distant points in the universe. The concept stems from the equations of general relativity, specifically those discovered by Albert Einstein and his colleague Nathan Rosen in 1935. According to their theory, a wormhole could connect two different regions of space-time, forming a bridge between them. The theory is elegant in its simplicity, a shortcut through the vast expanse of the universe, one that might enable time travel, interstellar exploration, or even the possibility of multiversal travel. But while the mathematics behind wormholes is compelling, the physical plausibility of their existence and use remains a topic of intense debate. Wormholes are imagined as tunnels with two ends, each situated in different locations in spacetime. These tunnels could, in theory, connect points in space, e.g. distant galaxies, or even different times. The simplest example is a traversable wormhole, often referred to as an Einstein-Rosen. In the original model, Einstein and Rosen described a wormhole as a connection between two black holes, with one end of the tunnel in the past and the other in the future. However, this basic structure faced immediate challenges. A traversable wormhole would require exotic matter with negative energy to remain open and stable, something not known to exist in the universe. The event horizon of black holes, which is an unavoidable boundary that nothing can escape from, also creates a barrier to travel. For a wormhole to be traversable, i.e., allowing passage through it, its mouths must remain open long enough to permit a traveler to enter. But this would require the manipulation of space-time in ways that are currently far beyond our technological capabilities. Theoretical physicists have since explored more refined models of wormhole, such as the wormhole solution to the Einstein field equations. These models suggest that space-time could bend in such a way as to create a passage between two regions of the universe. In theory, these tunnels could enable a shortcut that would allow objects to bypass the immense distances of space, making travel between distant stars or even galaxies an instantaneous feat. The mathematical elegance of this idea is undeniable, but the practicalities of creating or stabilizing such a structure remain highly speculative. Wormholes, as understood in modern physics, require conditions that we have yet to observe or create: exotic matter, negative energy, and the manipulation of space-time itself in ways we cannot currently replicate. The most significant challenge to the physical plausibility of wormhole is the issue of exotic matter. This theoretical substance is postulated to have negative energy density and would be required to keep a wormhole stable, preventing it from collapsing under the intense gravitational forces that would naturally arise from its curvature. Exotic matter would have properties contrary to ordinary matter. Its energy would behave oppositely, potentially allowing for the stabilization of a wormhole. However, negative energy has never been directly observed in nature. Some quantum theories, such as the Casimir effect, suggest that negative energy might exist at a quantum level, but there is currently no empirical evidence to support the large-scale existence of exotic matter needed to stabilize a wormhole. Moreover, even if we could somehow create a stable wormhole, the potential side effects of traveling through one remain largely unknown. The extreme gravitational forces near the mouths of a wormhole could create tidal forces that might stretch and compress any matter attempting to pass through it, potentially destroying anything that tries to enter. The idea that time travel could be possible via wormholes introduces another set of paradoxes, most notably the grandfather paradox, which questions the consequences of traveling back in time and altering events in the past. If a traveler were to alter the past through a wormhole, it could create a causal loop, challenging our understanding of determinism and the consistency of events. Despite these obstacles, the idea of wormholes offers tantalizing possibilities that cannot be easily dismissed. Some physicists believe that quantum mechanics might hold the key to resolving these issues, suggesting that quantum fluctuations could potentially allow for the creation of microscopic wormholes. These would be too small to be used by humans, but could provide insight into the fundamental nature of spacetime. Other theories propose that multiverses might be connected via wormhole, creating pathways between parallel universes. This leads to another speculative notion that wormholes could, in some form, be the bridges between universes, not just across space and time, but across dimensions. In conclusion, the wormhole hypothesis offers a glimpse into the potential future of space exploration, but its practicality remains highly uncertain. The elegance of the concept lies in its simplicity, offering a shortcut through the vastness of the cosmos, a way to bypass the limitations of time and space. However, the physical reality of wormholes faces enormous challenges, from the need for exotic matter to the theoretical implications of altering space-time. While the theory is compelling, we are still a long way from turning it into reality. Until we gain a deeper understanding of quantum gravity, exotic matter, and the fundamental nature of space-time, wormholes will remain as much a dream of the future as they are a mathematical curiosity of modern physics. The multiverse connection. The idea of black holes as gateways to parallel universes, or a multiverse, is one of the most fascinating and speculative concepts in modern physics. If black holes are indeed Einstein-Rosen bridges, wormholes linking distant regions of space-time, then perhaps they could also function as conduits between different universes. In this view, the singularities at the centers of black holes could be portals, not just to different points in space, but to entirely different universes, each with its own set of physical laws and constants. This concept challenges the traditional understanding of the universe as a singular, self-contained entity, proposing instead a multiverse of possibility. The concept of a multiverse arises from the idea that our universe is not the only one. Instead, there could be countless other universes, each with its own unique characteristics. Some of these universes might have entirely different laws of physics, where the constants of nature, such as the speed of light or the strength of gravity, vary in unimaginable ways. The idea that black holes could connect our universe to these other realms is rooted in theories of quantum mechanics, string theory, and cosmology, each of which suggests that the universe may not be as isolated as we once thought. One of the key ideas linking black holes and the multiverse is the concept of wormhole. According to the theory of general relativity, a wormhole is a shortcut through space-time connecting two distant points in the universe. If these wormholes could be traversable, they might allow for instantaneous travel between different regions of the universe, or, more speculatively, between different universes altogether. The event horizon of a black hole could be the entrance to such a wormhole, where matter and information are sucked into the singularity at the center of the black hole, potentially exiting through another universe via a parallel exit point. This idea ties into the holographic principle, which suggests that the three-dimensional nature of our universe could be encoded on a two-dimensional surface, like a hologram. If this principle holds, black holes may act as information storage devices, not only containing the information of the objects that fall into them, but also linking universes through these encoded surfaces. A multiverse of black holes could be interlinked, with each black hole serving as a node in a vast cosmic network. Matter and information traveling through a black hole could be transferred to an entirely different universe, allowing for the possibility of parallel worlds that share certain features, yet are governed by different laws. The concept of a multiverse where multiple universes exist in parallel, each with its own unique properties, presents a radical departure from the traditional view of a single, deterministic universe. In the multiverse model, the universe that we experience is only one of many possibilities. Some universes might be similar to ours, with similar laws of physics, while others could differ vastly, with alternate timelines or even entirely different dimensions of reality. This raises profound questions about the nature of reality and our place in the cosmos. Are we merely one outcome of countless possibilities, with each choice or event in our lives creating a new universe? Are there infinite versions of us, each living in a different parallel universe, experiencing different fates? While the concept of black holes as portals to parallel universes is still speculative, it offers tantalizing possibilities for our understanding of the universe and cosmology. If black holes could indeed serve as bridges between different realms, they might provide a deeper connection between quantum mechanics and general relativity, two of the most foundational yet incompatible pillars of modern physics. The idea of a multiverse might not only explain the mysteries of black holes, but also help reconcile some of the greatest unanswered questions in science, such as the fine-tuning problem, why the constants of nature seem so perfectly suited for life, and the nature of dark matter and dark energy. which continue to elude our understanding. The contrast between a single universe and a multiverse is stark. In a single universe, all events are interconnected, and the laws of physics govern everything within the same framework. In a multiverse, the potential for diversity is endless. Different universes might be created by random fluctuations in the early universe, or might arise from the varying outcomes of quantum events. Each universe could have its own rules, leading to a vast and potentially infinite range of possibilities. This idea challenges our very understanding of existence, suggesting that reality is not a single, deterministic path, but a complex web of potentiality, some of which may never be realized in our own universe, but exist in parallel universes nonetheless. While this theory remains speculative and far from proven, the idea of black holes as potential gateways to other universes presents a stunning vision of the cosmos, one where the universe is not a static, isolated entity but part of a much larger interconnected multiverse. Whether or not this theory is correct, the idea of a multiverse forces us to reconsider the nature of reality, suggesting that the universe we experience may be just one of many, each shaped by different conditions, constants, and possibilities. In this way, black holes could serve as both symbols and gateways to a deeper understanding of the universe and its hidden dimension, offering a glimpse into the unknown and a reminder that the cosmos is far more complex than we can even begin to imagine. The time travel hypothesis. The idea that a black hole could be a gateway to the past introduces one of the most exciting and perplexing possibilities in theoretical physics: time travel. Black holes and wormholes, with their mind-bending effects on space-time, offer a theoretical pathway to travel not just through space, but through time itself. The speculative theory hinges on the existence of closed time-like curves, CTCs, which are paths through space-time that loop back on themselves, allowing for travel into the past. While the notion of time travel raises numerous paradoxes and challenges, it remains a captivating area of study. The idea that black holes could lead to the past stems from the general theory of relativity. In relativity, space-time is not a static backdrop, but a dynamic entity that can be warped by massive objects like stars and black holes. When matter is concentrated to an extreme degree, such as within a black hole, space-time curves to such an extent that it might allow for closed time-like curves. These curves are loops in space-time that could, in theory, enable a traveler to return to a previous point in time. One of the speculative proposals for time travel involves wormhole, theoretical tunnels through space-time that connect distant regions or even different points in time. If such a wormhole were to exist and remain stable, it could potentially function as a bridge, allowing an object to enter the wormhole at one point in time and emerge in the past at another. However, this would require extreme conditions, such as the presence of exotic matter, to keep the wormhole open and prevent it from collapsing under its own gravity. Another theory involves rotating black holes, or Kerr black holes, which have the potential to form closed time-like curves near their event horizons. These black holes are unique in that their rotation twists space-time around them, possibly creating a situation where an object can travel along a loop through time, ultimately arriving at an earlier point in its own timeline. However, even if these time loops are theoretically possible, the practicalities of entering such a black hole without being destroyed by its immense gravitational forces are far from clear. Despite the fascinating implications of time loops and closed time-like curves, the possibility of time travel via black holes remains speculative. The paradoxes it introduces, such as the grandfather paradox, where a time traveler could alter events in the past, present significant challenges to our understanding of causality. Until these paradoxes are resolved, the idea of using a black hole to travel to the past remains one of the most intriguing yet unresolved questions in theoretical physics. The spaghettification effect. The spaghettification effect is one of the most vivid and chilling consequences of falling into a black hole. As an object or person nears the event horizon of a black hole, it encounters intense tidal forces that stretch and compress it along the direction of the gravitational pull. These forces are so extreme that they would ultimately stretch the object into a long, thin shape, like a strand of spaghetti, hence the term spaghettification. While this concept might sound like something out of a science fiction movie, it is a direct consequence of general relativity and one of the most peculiar features of black holes, revealing the profound difference between human experience and the extremes of physics at play near these cosmic phenomena. The event horizon is the point at which the gravitational pull of the black hole becomes so strong that not even light can escape. As an object approaches this boundary, the force of gravity increases exponentially. The closer one gets to the event horizon, the stronger the gravitational gradient, the difference in gravitational force from one part of the object to another. For a person falling toward a black hole, this gradient would stretch their body, elongating it in the direction of the black hole while compressing it sideways. The result is the spaghettification effect, where an astronaut or object is stretched thin like a piece of spaghetti and torn apart. As they get closer to the singularity, the forces responsible for spaghettification are tied to the immense tidal forces generated by the black hole's gravity. Imagine a person standing on Earth. The gravitational force they experience is nearly uniform across their body, meaning their head and feet experience almost the same gravitational pull. But near a black hole, the gravitational force changes dramatically over a very short distance. For example, a person's feet, which are closer to the black hole, will experience a much stronger pull than their head, which is farther away. This difference in gravitational forces stretches the body, pulling it apart, and spaghettification is the inevitable result. The human experience near the event horizon would be nothing short of terrifying. As you approach the black hole, time itself would begin to behave strangely. Due to the effects of gravitational time dilation, time would appear to slow down for the person falling in, relative to an outside observer. From the viewpoint of someone watching from a safe distance, the person falling toward the black hole would appear to slow down and eventually freeze near the event horizon, their image becoming more and more red-shifted until it vanishes from view. However, from the perspective of the person falling in, time would continue at a normal pace and they would pass through the event horizon, unaware of any changes in the flow of time. Once inside the event horizon, the person would be drawn closer to the singularity at the center of the black hole, where the gravitational forces become infinite. The tidal forces near the singularity would grow so strong that they would pull the person apart completely. The process of spaghettification would likely result in the complete destruction of the object long before reaching the singularity. It is unclear exactly how this destruction would unfold, but it is theorized that the person's body would be torn apart at a molecular level, with every atom stretched and compressed in a chaotic, violent process. The stretching forces of spaghettification are difficult to fathom because they contrast sharply with the human experience of gravity in our everyday world. We live in a universe where gravity, for the most part, is relatively mild, allowing us to move freely without feeling the strain of intense tidal forces. On Earth, we experience gravity as a constant, uniform force, and the difference in gravitational pull from our feet to our head is negligible. The forces we experience in daily life are gentle by comparison to the extreme gravitational gradients near a black hole. The experience of falling into a black hole is thus fundamentally different from anything we encounter in the familiar world. Yet, despite the seemingly impossible nature of spaghettification, it provides profound insights into the nature of space, time, and gravity as predicted by general relativity. Black holes and the tidal forces they create expose the limits of our physical theories, particularly when it comes to how objects behave in the extreme environment near the event horizon. The process of spaghettification underscores the dramatic consequences of warped spacetime, where the usual rules we take for granted in everyday life break down in the face of intense gravitational forces. While we cannot directly observe a person experiencing spaghettification, we can infer its effects through mathematical models and observations of phenomena like spaghettified stars or matter falling into black holes. In fact, the tidal forces of black holes are so extreme that they likely destroy any object long before it reaches the singularity. This is why any hypothetical journey to a black hole would end in destruction, rendering it impossible for any spacecraft or human being to survive the intense forces at play. In conclusion, The spaghettification effect provides a vivid illustration of how extreme physics near a black hole contrasts sharply with the normal human experience of gravity. While we can only imagine the terrifying effect of these tidal forces, their real-world consequences highlight the dangers of venturing too close to a black hole. The experience of falling into a black hole serves as a reminder of the raw power of the universe and the ultimate limits of human exploration in a cosmos governed by infinite gravity. The information paradox. The information paradox is one of the most profound and debated issues in modern physics, especially when it comes to understanding the nature of black holes. The paradox arises from the conflict between the laws of quantum mechanics and general relativity, two of the most fundamental frameworks in physics. According to quantum mechanics, information about the state of a system, such as the position and momentum of particles, must always be preserved. However, general relativity, when applied to black holes, suggests that anything that falls into a black hole is lost forever, including all of the information about the object. This apparent contradiction has led to one of the most significant unresolved questions in theoretical physics. What happens to the information that falls into a black hole? The core of the information paradox is this: black holes, with their event horizons and singularities, appear to destroy information. When matter and radiation fall into a black hole, they cross the event horizon and are thought to be irretrievably lost. Once past the event horizon, not even light can escape, meaning that the object's information is effectively hidden from the outside universe. According to classical general relativity, once something is inside the black hole, it is beyond reach. The laws of quantum mechanics, however, stipulate that information cannot be destroyed. This presents a problem. If black holes destroy information, it would violate the unitarity principle of quantum mechanics, which holds that the evolution of a closed quantum system should preserve information. This apparent conflict between general relativity and quantum mechanics leads to the information paradox. If a black hole evaporates over time through Hawking radiation, as predicted by Stephen Hawking in the 1970s, and if information is lost inside, then the loss of that information seems to contradict the fundamental principles of quantum theory. According to quantum mechanics, even when a system is transformed, all the information about the original system must still exist somewhere in the universe, albeit in a different form. This principle has been confirmed by numerous experiments, but it seems to be in direct opposition to the concept of black holes as information-destroying objects. The paradox has led to various theoretical proposals aimed at resolving the issue. One of the most prominent ideas is the holographic principle, which suggests that the information that falls into a black hole might be encoded on its event horizon, rather than being lost to the singularity. This would mean that black holes might not destroy information after all, but rather store it on their surface. According to the ADS-CFT correspondence, a conjecture from string theory, the behavior of a quantum system in a volume of space can be described by a theory that exists only on the boundary of that space. If this principle holds, the information inside a black hole could be encoded in a manner that preserves the laws of quantum mechanics, even if it is hidden from our view. Another theory that has been proposed to solve the paradox involves the idea of black hole complementarity. This concept suggests that information is not lost, but rather exists in different forms depending on the observer's perspective. For an observer falling into the black hole, it might seem like they pass through the event horizon without any noticeable effects, with the information preserved in some form. From an external observer's point of view, however, the information is scrambled and dissipated as the black hole evaporates through Hawking radiation. This approach posits that there is no contradiction because the information is both preserved and inaccessible in different frames of reference. However, despite these fascinating theories, the information paradox remains unresolved, and the debate over information loss and the laws of physics continues to be a central challenge in the search for a theory of quantum gravity. The true nature of black holes and the fate of the information they consume may ultimately reveal deep insights into the nature of space, time, and reality. Could black holes be the key to reconciling the mysteries of general relativity and quantum mechanics, providing a bridge between the macroscopic and microscopic descriptions of the universe? Or are we faced with a deeper paradox that cannot be resolved without a new framework altogether? The implications of the information paradox extend far beyond black holes. They touch on our understanding of reality itself. If information can be destroyed, it would imply that the universe is not entirely deterministic, and that fundamental laws of physics, such as conservation of information, might be violated at the quantum level. On the other hand, if information is always preserved, even in black holes, it could reveal something profound about the structure of the universe, possibly pointing toward a deeper layer of reality, where information is the true substance of the cosmos. In conclusion, the information paradox forces us to confront some of the deepest and most perplexing questions in physics. While significant progress has been made, the final resolution of the paradox remains elusive. Whether the solution lies in the holographic principle, black hole complementarity, or some entirely new framework, the debate underscores the limitations of our current understanding and the potential for future breakthroughs in the quest for a unified theory of quantum gravity. Could we ever survive? The question of whether technology or consciousness could survive crossing the event horizon of a black hole is one that strikes at the heart of both science and philosophy. While black holes remain one of the most fascinating objects in the universe, their extreme gravitational forces and the spaghettification effect make the prospect of survival seem implausible. However, in the realm of theoretical speculation, some ideas suggest that there might be ways, however unlikely, in which survival could occur, either through technological advancements or changes in our understanding of consciousness itself. As an object nears the event horizon, it is subjected to intense tidal forces. These forces become increasingly pronounced the closer you get to the black hole, stretching any object into a thin, elongated shape, a process known as spaghettification. For a human or a spacecraft, this means that the physical body would be stretched and torn apart long before reaching the singularity. The tidal forces near the black hole's core are so immense that nothing, not even the most advanced technology, could withstand the immense stress. No current material, no matter how robust, could remain intact in such an environment. Even if we could construct shielding to withstand radiation or gravitational pull, the fundamental structure of matter would be destroyed by the forces at play. However, some speculative theories posit that it's possible for certain kinds of information or consciousness to survive the crossing of the event horizon. In the holographic principle, it is proposed that all the information that falls into a black hole may be encoded on its event horizon, where it could potentially be preserved in a two-dimensional form. This raises the question, could consciousness, understood as a form of information processing, be similarly encoded and preserved even as the physical body is destroyed? If consciousness is purely informational, could it exist in some abstract form beyond the event horizon as a pattern of information that remains intact despite the destruction of the physical body? Moreover, theoretical technologies such as the manipulation of exotic matter or quantum teleportation might one day provide methods to survive or transcend the event horizon, though these ideas remain far beyond our current technological capability. The notion of using advanced technologies to preserve mental states or digital consciousness raises new, unsettling questions about the nature of life, death, and survival. In conclusion, while it seems highly improbable that we could survive crossing the event horizon with any physical form intact, future advancements in quantum mechanics or an understanding of consciousness might one day offer new insights into the possibility of surviving or even transcending the black hole's ultimate threshold. Time dilation. Near black hole, one of the most astonishing predictions of Einstein's theory of relativity is the phenomenon of time dilation, where time appears to move differently depending on the strength of the gravitational field or the velocity at which an observer is moving. Near a black hole, this effect becomes extreme. As an object approaches the event horizon, time seems to slow down relative to an observer far from the black hole. This warping of time isn't just theoretical, it's an intrinsic aspect of how the fabric of space-time behaves in the presence of intense gravity. However, while relativity's predictions are well supported by mathematical models and observations, they differ radically from the lived experience of those within the vicinity of a black hole. According to general relativity, time is not a constant universal measure, but something that is affected by the curvature of space-time. The greater the gravitational pull, the more space-time is curved, and the more time slows for an object in that field. Near a black hole, where gravity is intensely concentrated, this effect becomes extraordinarily pronounced. As an object approaches the event horizon, time appears to freeze from the perspective of an observer located far away from the black hole. The closer the object gets to the event horizon, the slower it seems to move in time, until, at the event horizon itself, time appears to stop altogether. From the perspective of someone falling into the black hole, however, time proceeds normally. For the astronaut or spacecraft traveling toward the event horizon, time would continue to move as it always does. They would not experience any dramatic slowing of their own perception of time. The difference in experience between the outside observer and the traveler is key to understanding the nature of time dilation near black holes. While an observer at a safe distance might see the astronaut's clock tick slower and slower as they approach the event horizon, the astronaut, on the other hand, would not notice any change in the passage of time for themselves. This discrepancy between the theoretical prediction and lived experience leads to some curious and unsettling implication. For the distant observer, as the astronaut gets closer to the event horizon, they would appear to move in slow motion, eventually seeming to freeze at the boundary of the black hole, never quite crossing it. However, for the astronaut, they would cross the event horizon as if nothing unusual had occurred, aside from the increasingly extreme tidal forces that would begin to stretch and compress them. In fact, according to general relativity, the crossing of the event horizon would seem almost uneventful to the traveler, at least from the standpoint of time perception. They would not experience time freezing, only the unstoppable fall toward the singularity. The differences between relativity's predictions and lived experience become particularly poignant when considering the ultimate fate of the object or individual crossing the event horizon. From the outside observer's point of view, the traveler's approach to the event horizon seems to take infinite time, meaning they would never actually witness someone crossing it. To the astronaut, however, their journey toward the singularity happens in finite time, and they would eventually reach the point where the gravitational forces become so extreme that they would be spaghettified, stretched, and torn apart as they approach the center of the black hole. The nature of time dilation also presents fascinating questions about the universal nature of time. While relativity tells us that time is subjective, the extreme effects of time dilation near a black hole force us to reconsider the absolute flow of time. In everyday life, we experience time as constant and uniform. We rely on clocks to measure the passage of time, and we take for granted that 1 second is the same as another. However, near a black hole, the very fabric of space-time bends in such a way that time becomes relative. The faster an object moves or the stronger the gravitational field it experiences, the more time slows. This means that in the presence of a black hole, time becomes more like a stretchable fabric, no longer a uniform constant, but a malleable part of the universe that is shaped by gravity. This extreme form of time dilation is also connected to time travel theory. If time slows down dramatically near a black hole, it opens up the possibility of traveling to the future. An astronaut spending only a few hours near a black hole might return to find that many years have passed on Earth, an unintended one-way journey into the future. While this is far from practical, it demonstrates how time dilation is intimately connected with the fabric of the universe itself, showing that time, like space, is not fixed but malleable depending on the gravitational condition of the surroundings. In conclusion, time dilation near black holes presents a profound and mind-bending distortion of reality as we know it. While general relativity offers precise and mathematically sound predictions, the lived experience of time near a black hole, whether for an external observer or someone falling in, reveals just how strange and non-intuitive the universe can be. Time is not the constant, unchanging force we perceive it to be in everyday life. Rather, it is a flexible, dynamic part of the space-time fabric that is influenced by gravity, making the passage of time as much a part of the cosmos's mysterious nature as any physical object. A journey to the past, the idea that black holes could offer a path for time travel, including the possibility of traveling backward in time, has long been a subject of speculation and fascination. According to general relativity, black holes warp space-time so dramatically that they might allow for the formation of closed time-like curves, CTCs, theoretical paths through space-time that loop back on themselves, potentially enabling a traveler to journey to the past. While time travel is still confined to the realms of theoretical physics and science fiction, the possibility that black holes might serve as gateways to the past introduces a profound question. Could a black hole provide the necessary conditions for backward time travel? And if so, how could it happen? The most well-known theoretical framework for time travel through a black hole is based on the concept of the Einstein-Rosen bridge, or wormhole. These hypothetical structures are theorized to connect two different points in space-time, either across vast distances in space or, more intriguingly, across different points in time. If wormholes could exist and remain stable, they could, in principle, serve as portals through time. A traveler entering such a wormhole at one point in time could potentially emerge at an earlier time in the universe's timeline. However, wormholes, like black holes themselves, pose a variety of theoretical and practical challenges. One speculative model involves the idea of a rotating black hole, or a Kerr black hole. These black holes are not static. They spin on their axis, twisting space-time in a way that could theoretically allow for the formation of a closed time-like curve. In this model, an object falling into the black hole would not be lost to the singularity, but instead could follow a path that loops back through time, emerging in the past. This concept is rooted in the equations of general relativity, which suggest that the rotation of a black hole can create a twist in space-time, leading to a path where the usual forward progression of time is disrupted and looped back on itself. While the mathematical models suggest that time travel might be possible through such black holes, they also come with significant paradoxes and unresolved questions. The most famous of these is the grandfather paradox, which questions what happens if a time traveler were to go back in time and alter past events, such as preventing their own birth. Would this create a causal loop? Would the traveler be able to change history? Or would the universe somehow correct itself to prevent such changes from occurring? These paradoxes illustrate the complexity and potential dangers of backward time travel, even in theoretical terms. Another speculative idea involves the use of exotic matter to stabilize a wormhole. According to current theories, a traversable wormhole would require negative energy, a form of matter that would have an opposite gravitational effect to that of regular matter. This exotic matter would theoretically prevent the wormhole from collapsing, as it might naturally do under intense gravitational forces. In the case of time travel, this exotic matter could maintain the wormhole's stability long enough to allow a traveler to pass through it, potentially traversing time as easily as they could traverse space. However, the existence of exotic matter remains purely theoretical, and no empirical evidence has been found to confirm its presence or practical utility. Despite these intriguing theories, there are significant practical limitations to time travel via black holes. The extreme gravitational forces near the event horizon would destroy any object that tried to cross it. Even if a wormhole were stable enough to allow passage, the process of entering a black hole would likely tear apart any matter that attempted the journey. This makes the prospect of human survival near or inside a black hole highly speculative. Furthermore, the sheer scale of the energy required to manipulate space-time in such a manner remains far beyond our technological capabilities. The physics of the quantum realm, which governs the behavior of particles at the smallest scales, could offer further insights into how time travel might work on a more fundamental level. But the unification of quantum mechanics and general relativity, the ultimate goal of modern physics, remains an unsolved problem. Despite the uncertainties and paradoxes, Black holes continue to serve as an important tool for exploring the nature of time and the universe. The possibility that they could provide a means of traveling backward in time invites us to reconsider our understanding of causality and the arrow of time. Could the discovery of stable wormholes or time loops one day change how we think about our past, present, and future? While we are still far from resolving the theoretical challenges of time travel, the idea that black holes might be a gateway to the past continues to inspire both scientific inquiry and philosophical reflection. In conclusion, while the notion of using black holes as a means of backward time travel is highly speculative, it represents a fascinating frontier in theoretical physics. Theories involving rotating black holes, wormholes, and exotic matter offer tantalizing glimpses into what might be possible if we can one day understand and manipulate the laws of space-time more profoundly. While much remains unknown, black holes remain a central piece of the puzzle in the quest to understand the nature of time and whether it is possible to move through it, backward and forward, as we do through space. Causal paradoxes. Time travel, particularly the idea of traveling backward in time, introduces a range of profound challenges to our understanding of causality, the relationship between cause and effect. If we could change events in the past, it would have dramatic consequences for the future, and this opens the door to several logical paradoxes. The most famous of these is the grandfather paradox, which asks, what happens if a time traveler goes back and prevents their own grandfather from meeting their grandmother? If the grandfather is never born, then the time traveler could never exist to travel back in time to prevent the meeting, creating a paradoxical loop of causality. How can events unfold logically when the very act of changing the past can create contradictory outcomes? The grandfather paradox is just one example of how backward time travel could challenge the linear progression of time and undermine our basic understanding of cause and effect. If time travel were possible, and if it allowed us to influence the past, causality, the very notion that causes precede effects, could break down. Every action taken in the past could ripple forward, altering the course of events and creating alternate timelines or even conflicting realities. This presents a fundamental problem. How could we account for all the consequences of our actions, and could time travel ever be consistent with the laws of logic? Causal loops, where an event is both the cause and the effect of another, are another complication introduced by time travel. Imagine a person who travels back in time and gives Shakespeare a copy of his own work, inspiring the famous playwright to write them. In this scenario, Shakespeare's works were both written by Shakespeare and by the time traveler, creating a loop with no clear origin for the works themselves. This raises the question of origin and whether events could ever truly be traced back to a beginning. Causal loops threaten the idea of a single, definitive timeline, and they suggest that time might not flow in a straightforward, linear fashion. These logical paradoxes are not just theoretical puzzles, they challenge the consistency of time travel as a concept. If we can alter the past, then what prevents us from creating infinite contradictions? The butterfly effect, where small changes can result in vastly different outcomes, becomes a potential minefield for time travelers. A seemingly minor action, like stepping on an insect in the past, could create a cascading series of events, leading to a completely altered present. If these alterations are allowed to happen, the notion of a consistent, ordered universe could be undermined. One potential resolution to these paradoxes comes from the many worlds interpretation of quantum mechanics. This theory posits that every time a decision is made or an event occurs, a new branch of reality is created. Instead of one timeline, there are multiple timelines or parallel universes, each one representing a different version of reality. If time travel is possible within this framework, then a traveler who goes back in time and changes an event would not alter their own past, but instead create a new timeline where the changes take place, while the original timeline remains intact. In this way, the grandfather paradox and causal loops could be avoided, as each change in the past would spawn a new branch of reality, ensuring that the original cause and effect remain undisturbed. Another approach to resolving time travel paradoxes comes from the self-consistency principle, which suggests that any changes made in the past must be consistent with the history that has already occurred. In other words, if you traveled back in time and tried to prevent your grandfather from meeting your grandmother, something would always happen to ensure that the event still occurs. Perhaps your time travel would fail, or some other event would intervene to preserve the timeline. This principle, proposed by physicist Igor Novikov, suggests that the laws of physics might enforce consistency in the timeline, preventing paradoxes from arising. While this resolution maintains causality, it limits the scope of potential changes a time traveler could make to the past, implying that history cannot be rewritten, only observed or nudged in subtle ways. While both the many worlds interpretation and the self-consistency principle offer plausible ways to avoid logical paradox, they introduce their own challenges and implications. The many worlds theory, for instance, leads to an infinite number of parallel universes, each with its own version of reality. This could result in a multiverse of parallel timelines, but it also raises the question of whether these universes are truly independent or interconnected in ways we do not yet understand. The self-consistency principle, while keeping a single timeline intact, would severely limit the possibilities for changing history and might even make time travel seem futile. Could we ever truly change the past if the universe insists on consistency? One potential implication of these paradoxes is that time travel might be fundamentally impossible, not because it violates the laws of physics, but because it leads to contradictions that the universe cannot sustain. Perhaps the very structure of causality, the rule that causes must precede effects, prevents time travel from ever being possible in a meaningful way. Time may be intrinsically one-directional and irreversible, ensuring that the past cannot be altered. No matter how advanced our technology becomes. In conclusion, the debate about causal paradoxes and time travel presents one of the most profound challenges in theoretical physics. The logical contradictions of events occurring in multiple timelines or within causal loops call into question the consistency of reality itself. While some theories, such as many worlds and self-consistency, offer potential solutions, they raise further philosophical and scientific issues. Whether time travel is possible or merely an interesting thought experiment, the consequences of time manipulation on causality underscore how deeply interconnected our understanding of time, physics, and logic truly is. Quantum entanglement and black hole. The concept of quantum entanglement has been one of the most puzzling and fascinating phenomena in the world of quantum mechanics. In a nutshell, quantum entanglement refers to a situation in which the quantum states of two or more particles become linked, so that the state of one particle instantly affects the state of the other, regardless of the distance separating. This phenomenon, first described by Albert Einstein as spooky action at a distance, fundamentally challenges our classical understanding of locality and causality. However, when combined with the mysterious nature of black holes, quantum entanglement takes on new and intriguing dimension, offering potential answers to some of the most profound questions in theoretical physics. In classical physics, information and interactions are understood in terms of local cause and effect relationships. When an object or particle moves or changes, it does so based on forces acting on it within the space it occupies. This understanding follows the framework of general relativity, which governs large-scale phenomena like gravity, black holes, and space-time curvature. In this classical picture, objects or events cannot influence each other instantaneously or faster than the speed of light. Information must travel across space at a finite speed. This principle aligns with the concept of locality, which states that physical processes are confined to specific regions of space-time. However, quantum mechanics introduces a completely different picture of reality. In quantum theory, particles can become entangled, meaning their properties, such as spin, position, or momentum, are no longer independent, even if the particles are separated by vast distances. When one entangled particle is measured, the state of the other particle is instantly determined, regardless of how far apart the two particles are. This concept defies classical intuition, where information is expected to propagate through space at a finite speed and seems to imply a non-local connection between distant particles. But how does this quantum behavior play out when applied to extreme phenomena like black holes, where space-time itself is dramatically warped and distorted? The intersection of quantum entanglement and black holes becomes especially significant when we consider the information paradox, a long-standing issue in black hole physics. According to general relativity, when an object or bit of information falls into a black hole, it is lost to the universe beyond the event horizon. However, quantum mechanics asserts that information can never truly be destroyed. This principle is known as unitarity. The question arises, if information is swallowed by a black hole, where does it go and how can it be reconciled with the law of unitarity? One of the proposed resolutions to this paradox is that quantum entanglement plays a crucial role in the behavior of black holes. Physicists, including Stephen Hawking and Juan Maldacena, have suggested that the entanglement of particles near a black hole could encode the information of anything that falls in. The key idea behind this is the holographic principle, which posits that all information contained within a volume of space can be described on its boundary, much like how a hologram encodes a 3D image in 2D space. This principle, if applied to black holes, suggests that information about anything that falls into a black hole is not lost, but rather encoded on the event horizon. Essentially, the surface of the black hole, the event horizon, might hold all the quantum information about the object or matter that has fallen inside, while the interior remains hidden. One way quantum entanglement is theorized to manifest near black holes is through a process called black hole complementarity. This hypothesis proposes that from the perspective of someone falling into a black hole, their information passes into the black hole, while an external observer would see the information encoded on the event horizon as the object approaches. This duality is made possible by quantum entanglement, which allows information to exist in multiple forms, simultaneously one form inside the black hole and another on the event horizon. The result is that the information is preserved even though it seems to vanish into the singularity. Despite the elegance of these theories, they are still highly speculative, and many questions remain unanswered. For instance, if the information is encoded on the event horizon, how can we ever access it from outside the black hole? And if the entanglement of particles near a black hole can preserve information, does it mean that black holes are not actually destructive, but rather transformative? Could the quantum entanglement near the event horizon represent a bridge between different regions of space-time, or even between parallel universes, as some hypotheses suggest? The role of quantum mechanics near black holes also leads to questions about the nature of space and time itself. If quantum entanglement can influence space-time on such extreme scales, does this mean that space-time is not a smooth continuum, as general relativity suggests, but is rather discrete at the quantum level? Could the fabric of space-time be woven together by the entanglement of quantum particles, creating a more complex and interconnected universe than we can currently imagine? In this view, black holes might not be the ultimate destroyers of information, but instead a gateway to new forms of reality, where the boundaries between space, time, and information are blurred. In conclusion, quantum entanglement and black holes represent a fascinating intersection of the known and the unknown in modern physics. While classical physics tells us that black holes are information sinks, quantum mechanics and the holographic principle suggest that the information might be preserved, encoded on the event horizon itself. This interplay between general relativity and quantum theory is central to the quest for a unified theory of physics and may eventually lead to a deeper understanding of the nature of reality. The unresolved questions about the relationship between black holes and quantum entanglement keep physicists searching for new insights into the most fundamental aspects of the universe. The holographic principle. The holographic principle is one of the most mind-bending ideas in theoretical physics, proposing that the three-dimensional universe we perceive may not be the full picture. Instead, it suggests that all of the information about the universe could be encoded on a two-dimensional surface, much like how a hologram encodes 3D images in 2D space. This principle emerged from the study of black holes and quantum gravity, where it offers a potential resolution to the information paradox, the long-standing debate about whether information that falls into a black hole is lost forever. The idea is that information, instead of being destroyed at the event horizon, is encoded there, preserving the laws of quantum mechanics and solving one of the biggest mysteries in physics. At the heart of the holographic principle is the realization that black holes behave as though the three-dimensional space within them can be represented as a two-dimensional structure. The first hint of this came from the study of black hole thermodynamics, specifically the relationship between the entropy of a black hole and the surface area of its event horizon. In classical physics, entropy is a measure of the number of possible microscopic configurations of a system. In the case of black holes, it was found that the entropy is proportional to the area of the event horizon, not the volume enclosed by it, suggesting that the information inside the black hole could be encoded on its surface. This idea was formalized in the ADS-CFT correspondence, a conjecture from string theory proposed by Juan Maldacena in 1997. The ADS-CFT correspondence suggests that a theory of gravity in a d-dimensional spacetime can be described as a quantum field theory on a d1-dimensional boundary. Essentially, this means that the three-dimensional reality we experience could be a projection of a two-dimensional theory that resides on the boundary of the universe. This was a radical shift in thinking, implying that the information about everything in the universe could, in principle, be stored on the two-dimensional surface of the event horizon of a black hole. The implications of the holographic principle extend far beyond black holes and into the nature of space-time itself. If the universe is fundamentally two-dimensional, then our perception of a 3D world is just a projection of that lower-dimensional reality. In this view, the fabric of space-time is like the surface of a hologram, where everything we observe, objects, forces, even the passage of time, are merely projections of information encoded on a distant boundary. This is difficult to grasp because we live in a universe that seems inherently three-dimensional, with depth, width, and height all readily apparent. But according to the holographic principle, what we perceive as 3D space could simply be a manifestation of a deeper 2D reality that we cannot directly observe. This idea challenges our basic assumptions about space and time. In the traditional view of physics, we consider space and time as continuous fundamental components of the universe. Yet, the holographic principle suggests that they may not be fundamental at all, but rather emergent properties of a deeper, underlying reality. If this is the case, then our entire understanding of the universe, our perceptions of reality, location, and movement could be based on an illusion, a projection of information encoded on a two-dimensional surface, much like the 3D images we perceive from a 2D hologram. The implications for black holes are equally profound. If the holographic principle holds true, then the event horizon of a black hole is not merely a boundary that separates the interior from the rest of the universe. Instead, it is a membrane where all the information about the matter that has fallen into the black hole is stored. This means that information is not lost when an object crosses the event horizon, but instead preserved in a form that we cannot directly access. The seemingly paradoxical situation of information disappearing into the black hole is resolved by the idea that it is encoded on the event horizon, where it can remain intact even as the interior of the black hole is hidden from view. The holographic principle also raises important questions about the nature of the universe itself. If the universe is fundamentally 2D in nature, how does this relate to the larger cosmological questions about space and time? Could it be that the universe is part of a much larger structure and the 3D reality we perceive is merely a projection from a deeper dimension? These questions challenge our very understanding of existence and reality, suggesting that space and time are not fundamental, but emergent from more basic quantum processing. While the holographic principle remains speculative and is not universally accepted, it provides a powerful framework for understanding some of the deepest questions in physics. It offers a potential solution to the black hole information paradox, suggesting that the information swallowed by a black hole is not lost, but instead encoded on its event horizon. This principle has profound implications not only for the study of black holes, but for our understanding of quantum gravity, space-time, and the nature of the universe itself. In conclusion, the holographic principle challenges the way we think about space and time, offering the possibility that our 3D universe is merely a projection of a deeper 2D reality. It provides a potential resolution to the paradox of information loss in black holes and opens up new avenues for exploring the fundamental nature of reality. If proven correct, it could revolutionize our understanding of the universe and our place within it, fundamentally altering how we think about the fabric of space-time and the very nature of existence. Black holes as time machine. The idea of black holes as time machine is one of the most speculative and intriguing aspects of modern theoretical physics. In the context of general relativity, black holes are traditionally seen as cosmic death traps where nothing, not even light, can escape once it crosses the event horizon. However, quantum theories, particularly those involving wormholes and closed time-like curves, CTCs, suggest that black holes might also serve as gateways to time travel, both to the future and possibly the past. Of the most famous speculative theories regarding black holes as time machines is rooted in the concept of the Einstein-Rosen bridge, more commonly known as a wormhole. A wormhole is a hypothetical tunnel through space-time that connects two distant points in space or time. If these wormholes could be stabilized, they could serve as shortcuts through space, allowing for instantaneous travel between distant regions. But more tantalizingly, wormholes could potentially allow for travel backward in time, depending on how they are manipulated. In a rotating black hole or Kerr black hole, the situation becomes even more interesting. The rotation of a black hole causes a twisting of space-time, and under certain conditions, it could create a closed time-like curve, CTC. In this scenario, an object or person could fall into the black hole, and instead of being destroyed by the singularity, they might emerge at an earlier point in time. The mathematical model suggests that the rotating black hole could be connected to a different region of space-time through the wormhole-like structure, forming a loop that allows for time travel into the past. Though these ideas are grounded in the equations of general relativity, they remain speculative, as we have no experimental evidence to suggest that they are physically possible. Another speculative theory involves quantum mechanics and the holographic principle. Some physicists believe that quantum entanglement and the concept of information preservation in black holes might provide a new way to think about time travel. If information about the past is preserved in the quantum states of particles within or near the event horizon, could that information be accessed and used to navigate time in a non-traditional sense? This would not necessarily involve traveling through time as we intuitively understand it, but might allow us to retrieve information from the past, or even use the quantum properties of black holes to alter timelines in unforeseen ways. While these theories remain speculative, they underscore the fact that black holes are not only cosmic objects of destruction, but potentially windows into deeper realms of physics and time itself. If ever proven, black holes might indeed be more than just celestial death traps. They could one day serve as time machines, capable of transporting us across the vastness of both space and time, challenging our understanding of causality and the very flow of the universe. The black hole information paradox. The black hole information paradox is one of the most fundamental and unresolved questions in modern physics. At its heart lies a contradiction between general relativity, which governs the behavior of massive objects like black holes, and quantum mechanics, which governs the behavior of the smallest particles. The paradox centers on whether information that falls into a black hole is truly lost or whether it is preserved in some form. The stakes of resolving this paradox are high because the resolution may hold the key to reconciling general relativity and quantum mechanics, two pillars of physics that have yet to be unified into a single theory of quantum gravity. According to general relativity, when matter and information are swallowed by a black hole, they are irretrievably lost. This is due to the event horizon, the boundary beyond which nothing can escape, not even light. The intense gravitational forces near the event horizon cause the collapsing matter to be crushed into a singularity, a point of infinite density. Within this framework, once something crosses the event horizon, all information about its physical state is lost to the universe. From the perspective of classical physics, this creates an ultimate form of entropy, where all traces of the matter's history are erased. However, this view contradicts a fundamental principle of quantum mechanics. Information cannot be destroyed. Quantum theory holds that the information about the state of a system, the positions, velocities, and quantum states of its particles should always be preserved, even if the system undergoes a transformation. This principle is known as unitarity, and it is essential for the consistency of quantum mechanics. If information could be lost in a black hole, it would violate this foundational tenet of quantum theory, implying that the laws of physics are not fully consistent across different scales. This is the essence of the black hole information paradox. How can information be both lost, as general relativity suggests, and preserved, as quantum mechanics demand? This paradox became particularly apparent in the 1970s when Stephen Hawking proposed that black holes emit radiation, now known as Hawking radiation, due to quantum effects near the event horizon. This radiation, which is made up of particles and antiparticles, would carry away mass from the black hole, leading to its gradual evaporation. Hawking's prediction sparked a significant controversy. If a black hole can lose mass and eventually evaporate, and if all information about the objects that fall into it is lost, what happens to the information that the black hole consumes? If the information is destroyed during the evaporation process, it would violate the no-cloning theorem of quantum mechanics, which states that information cannot be duplicated or erased. In response to this paradox, several speculative theories have emerged in an attempt to preserve the principle of unitarity and reconcile the conflicting views of quantum mechanics and general relativity. One such theory is the holographic principle, which suggests that all the information contained within a black hole might actually be encoded on its event horizon, rather than being lost inside the singularity. According to this idea, the surface area of the event horizon, rather than the volume inside the black hole, holds all the information about the matter that has fallen in. This would mean that while the matter inside the black hole is hidden from the outside world, its information is still preserved in a different form, stored on the black hole's surface. This concept is supported by the ADS-CFT correspondence, a framework from string theory that relates gravitational theories in a bulk space to quantum field theories on the boundary of that space. In the case of black holes, the boundary is the event horizon, which might store the information in a two-dimensional form that is equivalent to the three-dimensional reality inside the black hole. Another speculative solution is black hole complementarity, which proposes that the information inside a black hole is not lost, but exists in different forms depending on the observer's perspective. For an external observer, the information might appear to be smeared across the event horizon and gradually dissipated by Hawking radiation. Meanwhile, for someone falling into the black hole, the information could remain intact inside the black hole, preserved in the form of quantum states. In this way, both viewpoints are true in their respective frames of reference, and the information paradox is avoided by asserting that the information is both encoded on the horizon and inside the black hole, depending on the observer. Despite these theories, the resolution of the black hole information paradox is far from settled. Some physicists believe that the information may indeed be lost and that the laws of quantum mechanics may need to be revised or expanded to accommodate the unique nature of black holes. This approach, known as information, would suggest that black holes are fundamentally different from other quantum systems and that the standard principles of quantum theory cannot be directly applied to them. Others argue that the paradox will ultimately be resolved by a deeper theory of quantum gravity that unifies general relativity and quantum mechanics, providing a more comprehensive understanding of black holes and the nature of information. Ultimately, the black hole information paradox represents one of the most profound challenges in the search for a unified theory of the universe. Whether the information inside a black hole is lost, encoded, or preserved in some other form, resolving the paradox will likely reveal important insights about the nature of space, time, and quantum reality. Until a theory of quantum gravity is fully developed, the question of whether information can be lost in a black hole remains one of the most tantalizing mysteries in theoretical physics. The no-hair theorem vs. quantum consciousness. The no-hair theorem and theories of quantum consciousness present two contrasting views of complexity and information in the universe, one rooted in the structure of black holes and the other in the nature of human consciousness. At first glance, these concepts appear unrelated. The no-hair theorem suggests that black holes are incredibly simple, reducing all matter and information that falls into them to just a few basic parameters: mass, charge, and angular momentum, while quantum theories of consciousness suggest that consciousness arises from complex, dynamic quantum processes that could encode vast amounts of information. Yet, when considered together, these ideas invite us to explore profound questions about the nature of simplicity and complexity in both the physical universe and mind. The no-hair theorem is a principle in general relativity that states that black holes, regardless of the matter that falls into them, are completely characterized by just three observable properties: mass, electric charge, and angular momentum. According to the theorem, black holes do not retain any other distinguishing characteristics, such as the specific information about the objects that fall into them. This loss of information has been one of the central puzzles of black hole physics, as it implies that once matter crosses the event horizon of a black hole, all the details about that matter, its shape, composition, and other unique properties are erased, leaving only the three aforementioned parameters. In essence, black holes, despite their incredibly dense and energetic nature, become incredibly simple objects, devoid of any hair or complexity. This simplicity is in stark contrast to the complexity found in systems like human consciousness. Quantum consciousness theories, such as those proposed by Roger Penrose and others, suggest that consciousness arises from the quantum states of the brain's particles, involving vast amounts of information and entanglement. According to these theories, the brain is not just a classical computational system, but a quantum system that harnesses the strange and intricate behaviors of quantum mechanics, such as superposition and entanglement, to process information. This theory suggests that consciousness is not a simple output of neural activity, but is instead a highly complex phenomenon that requires an understanding of quantum processes and their ability to store, process, and manipulate vast quantities of information. The contrast between the simplicity of a black hole and the complexity of quantum consciousness raises profound questions about how information is processed and preserved in the universe. The no-hair theorem implies that black holes effectively erase the information about matter that falls into them, while quantum consciousness theories suggest that information is fundamental to the very nature of conscious experience. If black holes are information sinks, how do we reconcile this with the idea that information is fundamentally preserved in quantum systems like consciousness? Could the universe itself, like a black hole, be a repository of information that is lost, encoded, or transformed in ways that we do not yet understand? One speculative bridge between these two ideas comes from the study of black hole entropy. The Bekenstein-Hawking entropy suggests that black holes, despite their apparent simplicity, have a very high degree of quantum complexity. Their entropy is proportional to the surface area of the event horizon, not the volume inside. This idea has led to the notion that the event horizon might encode all of the information about the matter that has fallen into the black hole, suggesting that even in the simplest black hole, the encoded complexity of the universe might be preserved. Could this idea have parallels in consciousness? Just as a black hole's event horizon might encode vast amounts of information about the matter inside it, perhaps consciousness itself encodes information about the mind and the experiences that comprise it, with quantum coherence acting as a kind of horizon in the brain where information is stored and processed. This comparison suggests a fascinating parallel. Just as black holes seem to simplify and reduce all matter to three key properties, might human consciousness similarly condense the complexities of experience, memory, and perception into a form that can be processed by the brain's quantum systems? If black holes and consciousness are both information systems, then the way we understand the preservation and processing of information in the quantum realm could help unlock a deeper understanding of both black hole physics and the nature of the mind. However, there are important differences between these concepts. While the no-hair theorem implies that black holes ultimately reduce everything to a simplified state, quantum consciousness theories suggest that consciousness emerges from complex quantum processes that involve the interaction of vast numbers of particles and quantum states. The simplification inherent in black holes contrasts sharply with the emergent complexity of consciousness, where intricate and non-linear interactions produce the richness of human experience, thought, and perception. Another crucial distinction lies in the nature of information in these two systems. In black holes, the information is said to be encoded on the event horizon, which implies a loss of certain kinds of details about the objects inside. In quantum consciousness, however, the information about the self and the world around us is continually processed, interpreted, and restructured, creating an evolving, dynamic system of perception. While black holes may appear to destroy information, quantum consciousness allows for a continual flow and processing of information, without any loss of fundamental properties. In conclusion, the juxtaposition of the no-hair theorem and quantum consciousness theories invites us to explore the tension between simplicity and complexity in the universe. While black holes, as described by the no-hair theorem, seem to reduce information to its most basic elements, quantum theories of consciousness suggest that the mind thrives on the complexity of quantum processes. These contrasting ideas raise profound questions about the nature of information, the fate of the universe, and the fundamental structure of reality itself. Do we live in a universe where complexity is always preserved, or are there limits to how much information can be retained, whether in the fabric of space-time or in the workings of the mind? The infinite impossibility. While the idea of black holes as gateways to other dimensions or time travel portal captures the imagination, many physicists remain deeply skeptical about such claim. The allure of black holes as potential conduits to alternate realities or time periods is tantalizing, but skepticism arises from the extreme conditions near black holes and the lack of empirical evidence to support these speculative ideas. In the eyes of many scientists, these ideas represent more of a philosophical puzzle or science fiction, rather than something grounded in practical reality. First and foremost, general relativity, which governs the behavior of black holes, predicts that anything crossing the event horizon is irretrievably lost to the singularity. From a classical physics perspective, once an object falls into a black hole, it is crushed to infinite density at the singularity, where the laws of physics as we know them break down. The intense gravitational forces near the event horizon also prevent anything from escaping, including light. This makes the notion of a black hole acting as a gateway for time travel or interdimensional travel seem highly implausible. If everything that crosses the event horizon is destroyed, how could any information, let alone a person, survive to travel through time or across dimensions? Furthermore, the mathematical models used to describe black holes do not show any viable way for wormholes or closed time-like curves to exist in a stable, traversable form. While some theoretical solutions to Einstein's field equation suggest that black holes might create such structures, these are often highly idealized or come with extreme caveats, such as the need for exotic matter to stabilize a wormhole. Even then, the existence of such exotic matter remains unconfirmed by experimental data. Without concrete evidence that wormholes or time loops could be created or navigated in the real universe, many physicists view the idea of black holes as time machines as a mathematical curiosity rather than a realistic scenario. Additionally, the lack of observational evidence for any phenomena that could suggest the existence of time travel through black holes further fuels skepticism. If black holes were truly portals to other universes or time periods, we would expect to see observable effects in the behavior of matter and energy around them. However, despite decades of research and observations, no such phenomena have been detected. In fact, the event horizon itself is essentially a one-way barrier, and current theories suggest that even if we could theoretically enter a black hole, the intense tidal forces and eventual spaghettification would destroy any object long before it could cross into another time or dimension. Quantum mechanics also raises its own set of concerns about the viability of time travel through black holes. While quantum entanglement and quantum tunneling have demonstrated bizarre and counterintuitive behaviors at small scales, these effects have not been observed to operate on the macroscopic scale of black holes. Quantum gravity, which would be required to reconcile general relativity with quantum theory, remains an unsolved problem in physics. Until a unified theory of quantum gravity is developed, the speculative nature of black holes as time portals remains just that, speculation. Finally, many physicists argue that black holes should be viewed through the lens of pragmatic realism rather than as gateways to fanciful possibilities. The study of black holes is crucial for understanding extreme environments, space-time, and gravity, but it is also an opportunity to investigate the limits of our understanding. Instead of assuming black holes are mysterious portals or time machines, some physicists prefer to focus on more testable aspects, such as Hawking radiation and the information paradox, which may offer deeper insights into the fundamental laws of the universe. In conclusion, while the idea of black holes as time travel portals is captivating, it remains a theoretical fantasy in the eyes of many scientists. The extreme conditions around black holes, the lack of empirical evidence, and the unresolved problems in quantum gravity all point to the improbability of such claims. Until we develop a more comprehensive understanding of quantum mechanics, general relativity, and the nature of black holes, the notion of black holes as gateways to other times or dimensions remains firmly within the realm of speculative fiction rather than scientific fact. The black hole as a passage to another universe. The idea of black holes as passages to other universes has fascinated both theoretical physicists and science fiction writers for decades. The concept arises from the understanding that black hole, while representing one of the most destructive forces in the universe, may also harbor profound secrets about the nature of space-time and the potential for alternate reality. According to some speculative theoretical models, black holes might not just be regions where everything is destroyed, but could instead act as gateways to other universes, each with its own set of laws of physics, constants, and potentially even dimensions. Could a black hole lead to the creation of a new universe or serve as a bridge to a parallel one? These ideas are speculative, but they offer tantalizing possibilities about the structure of the cosmos. The notion that black holes could lead to other universes is tied to the concept of the multiverse, a theory that suggests our universe may not be the only one. The multiverse theory proposes that there could be an infinite number of universes, each with its own distinct properties. These universes could have different laws of physics, alternative constants, and even different spatial dimensions. One potential mechanism for the creation of new universes comes from eternal inflation, the idea that the universe is continuously undergoing inflationary expansion in some region, creating new bubbles or pocket universes that each have their own separate existence. In this model, black holes could play a critical role in the formation of new universes. Some cosmological models suggest that the singularity at the center of a black hole could act as a point of transition into a different region of space-time, creating conditions where a new universe could begin. This process might be analogous to the birth of our own universe during the Big Bang, where a singularity gave rise to a vast expansion of space. In this view, the collapse of matter into a black hole may not represent the end of a system, but rather a birth point for a new universe, potentially connected to ours through the black hole's event horizon. The idea that black holes might serve as portals to other universes is often explored through wormhole theories, which suggest that a wormhole might form at the event horizon of a black hole. A wormhole is a theoretical tunnel through space-time that connects distant parts of the universe or even different universes altogether. The connection between a black hole and a wormhole suggests that the gravitational forces at the black hole's core could serve as a bridge linking our universe with another, allowing for the possibility of matter and energy traveling through these cosmic tunnels. If such wormholes exist, they could theoretically provide a gateway to parallel universes, each with its own unique characteristics. This idea is supported in part by quantum mechanics and string theory, which suggest that space-time may not be a simple, continuous entity, but instead could consist of multiple dimensions. Some string theory models propose that black holes could be connected to higher dimensional spaces, possibly offering access to parallel reality. In such scenarios, black holes could be seen as windows to other realms of existence, possibly even dimensions that are hidden from our current perception of space and time. Moreover, theoretical physicists have speculated that the information paradox, the debate over whether information is lost inside a black hole or preserved in some way, might offer clues. Black holes could lead to alternate universes. If information is preserved in the form of quantum entanglement or encoded on the event horizon, as suggested by the holographic principle, it could imply that black holes don't merely destroy information, but may transform it, creating a new space-time region that is separate from our own. In this view, the information about an object that falls into a black hole is not lost, but might be transferred into a new universe, where it is reorganized according to different laws of physics. Despite these intriguing theoretical possibilities, the idea of black holes as passages to other universes remains speculative and faces numerous challenges. One of the biggest issues is the stability of wormholes. In most models, wormholes are highly unstable and would collapse before anything could pass through them. Some theories propose the existence of exotic matter, a form of matter with negative energy that could stabilize a wormhole, but such matter has never been observed in nature. Additionally, the extreme conditions inside black holes, especially near the singularity, remain beyond our current understanding of physics, particularly without a unified theory of quantum gravity that could combine general relativity and quantum mechanics. Another challenge lies in the fact that black holes are inherently one-way objects. The event horizon, which marks the boundary of the black hole, is the ultimate point of no return. Once something crosses the event horizon, it is drawn inexorably toward the singularity, where all known laws of physics break down. For an object to travel from one universe to another via a black hole, it would have to survive the immense tidal forces and extreme conditions near the singularity, something that seems practically impossible given our current understanding of spaghettification and other relativistic effects. In conclusion, the idea that black holes could serve as gateways to other universes is a fascinating speculative theory that touches on the deepest questions about the nature of the cosmos. While we have no experimental evidence to support the idea that black holes can create new universes or serve as portals to parallel realities, the possibility remains an exciting area of research in both cosmology and theoretical physics. Whether black holes are truly connected to the birth of new universes or simply the end points of massive objects in our own universe, they continue to be one of the most intriguing and enigmatic features of the cosmos, challenging our understanding of space, time, and reality itself. The end of space and time, the region beyond the event horizon of a black hole, remains one of the most mysterious and mind-bending areas of modern theoretical physics. According to general relativity, once anything, be it matter, light, or information, crosses this boundary, it is lost to the universe. However, this is not the only view of what happens at the edge of a black hole. Speculative theories suggest that space and time behave in radically different ways beyond the event horizon, potentially leading to a redefinition of our understanding of reality. What lies beyond the event horizon? Is space and time as we know it annihilated, or do they continue to evolve in unknown ways? These questions push the boundaries of physics and challenge the very fabric of the universe. One of the most striking speculations about the nature of space and time beyond the event horizon comes from the idea that space and time may become interchangeable. Under normal conditions, time flows in one direction, from past to present to future, while space expands and contracts. However, at the event horizon of a black hole, the equations of general relativity suggest that this symmetry could break down. As an object approaches the event horizon, time appears to slow down relative to an external observer, and the forces of gravity warp space in such a way that they become indistinguishable. In the final moments before crossing the event horizon, the lines between space and time might blur to the point where the future becomes as inescapable as the present, an unnerving idea for any observer caught in the grip of a black hole. This concept of space-time reversal is explored in the maximal gravitational singularity, the core of it. Once past the event horizon, the singularity at the center may represent a point where space itself becomes a temporal dimension, where the direction of time is no longer intuitive. In essence, the singularity could act as a singular moment in time, where all the laws of physics collapse into a singular point, and time becomes stretched infinitely in all directions. If this model holds true, then beyond the event horizon, the standard structure of space-time could no longer exist as we know it. Instead of a three-dimensional expanse, it could become a timeless, boundless realm, where the usual distinctions between time and space dissolve. Another speculative possibility about what happens beyond the event horizon stems from the holographic principle and the idea that all information about a black hole, what falls into it, and what surrounds it is encoded at the event horizon. According to the holographic principle, the entire interior of a black hole might be a projection of information stored on the 2D surface of the event horizon. This suggests that beyond the event horizon, space and time might not be as we know them. Instead, they could be encoded in 2D information that is woven together to create the illusion of a 3D world. This raises the question, is the experience of space and time inside a black hole simply an illusion, a projection of data that we cannot yet understand? Are the rules of cause and effect fundamentally altered in this new realm? Moreover, the idea that quantum mechanics could play a major role in shaping the nature of space and time inside black holes further complicates our understanding. The quantum nature of matter and energy suggests that uncertainty and probability govern the fundamental behaviors of particles, and that the concept of determinism may break down in extreme environments like the singularity. Quantum fluctuations near the event horizon might give rise to new and previously unobserved phenomena, where the very fabric of space-time could flicker, creating temporary anomalies that defy classical notions of space and time. These quantum effects could blur the boundaries of space and time, allowing for non-locality where events that are distant in space could influence each other instantaneously, further complicating our understanding of what happens beyond the event horizon. Other speculative ideas include the possibility that the inside of a black hole could be connected to a parallel universe or even represent the birth of a new universe. This concept, often referred to as the baby universe hypothesis, suggests that the singularity at the center of a black hole might serve as a point where a new, separate universe could emerge. In this view, the black hole is not a final point of destruction, but rather a seed for new space-time regions that evolve into independent cosmological systems. The collapse of matter into the singularity would, in this sense, serve as the foundation for new realities governed by their own laws of physics. Despite the mathematical models that support these speculative theories, the reality of what actually occurs inside a black hole remains elusive. The breakdown of the laws of physics near the singularity, combined with the extreme conditions of gravity, make it nearly impossible to observe or measure directly. Even the quantum mechanics that govern the microscopic world cannot fully explain the behavior of space-time near the event horizon, as a unified theory of quantum gravity which could explain both general relativity and quantum mechanics remains out of reach. In conclusion, the question of what happens to space and time beyond the event horizon of a black hole challenges our understanding of the fundamental structure of reality. Speculative theories suggest that time and space may lose their familiar properties, becoming intertwined in unexpected ways or even giving birth to new universes. Whether black holes are windows into alternate realities, realms of infinite potential, or mere cosmic dead ends, they remain one of the greatest mysteries in physics, prompting further exploration and deeper questions about the nature of the universe itself. For now, the end of space and time remains beyond the reach of our observation, a final frontier in the study of the cosmos. The Big Bang revisited the idea that black holes could serve as portals to the beginning of our universe, or perhaps to the end of another, is an intriguing and speculative possibility in modern cosmology. The Big Bang, the event that marks the origin of our universe, is traditionally viewed as a singularity, a point of infinite density where space and time began. But what if black holes are not just cosmic objects of destruction, but also gateways to the beginning or end of entire universes? Could the collapse of matter into a black hole be connected to the birth of a new universe, just as the Big Bang led to the birth of our own. One hypothesis, often referred to as the baby universe theory, suggests that black holes could function as portals through which new universes are born. In this view, the singularity at the center of a black hole is not the ultimate destruction of matter, but rather a transition point to a new, separate universe. This concept is supported by certain models of eternal inflation, which propose that the universe is in a constant state of inflation, continually creating new pocket universes. According to this model, the intense gravitational forces within a black hole could create conditions where a new universe might begin with its own set of physical laws separated from our own. Thus, the collapse of matter in a black hole could serve as the origin of another cosmic realm. On the flip side, black holes could also represent the end of a universe. If the material that falls into a black hole is compressed into a singularity, it could imply that the end state of a universe might involve the formation of a black hole, a point where space and time break down. Some speculative theories propose that the black hole could be the endpoint of a closed universe, where space-time contracts and eventually collapses into a singularity, marking the death of that universe. In this sense, the black hole could be a cosmic reset button, where the cycle of birth and death of universes continues, much like a cosmic loop. Whether black holes are actually portals to the beginning or end of universes remains an open question, but these ideas offer profound insights into the interconnectedness of the universe's life cycle. Ultimately, they challenge our perception of space, time, and cosmic evolution, suggesting that black holes may play a role in shaping the universe in ways we have yet to fully understand. Consciousness as a quantum phenomenon. The question of what constitutes consciousness has puzzled philosophers, scientists, and thinkers for centuries. While there have been many theories about its origins and nature, one of the most intriguing and speculative ideas in modern science is that consciousness itself may be a quantum phenomenon. In this view, consciousness is not merely a byproduct of complex neural networks or biochemical processes, but rather something that emerges from the behavior of particles at the quantum level, a hypothesis that could potentially bridge the gap between the physical and the non-physical aspects of the mind. This theory contrasts sharply with the traditional view of consciousness as a physical phenomenon arising from the brain's neural activity, and it raises deep questions about the very nature of reality and the relationship between mind and matter. The quantum consciousness hypothesis posits that the fundamental processes of consciousness involve quantum mechanical systems, such as superposition, entanglement, and wave function collapse. This perspective finds its roots in the work of Roger Penrose and Stuart Hameroff, who proposed the orchestrated objective reduction (OR) theory. According to OR, consciousness arises from quantum computations occurring in the microtubules, tiny structures within neurons that are involved in the process of cell division and intracellular transport. These quantum computations, Penrose and Hameroff argue, are non-algorithmic and occur outside the realm of classical physics, meaning that conscious experience cannot be reduced to mere computational processes. One of the core features of the quantum consciousness theory is the non-local nature of quantum mechanics. In classical physics, we think of particles and systems as being localized, existing at a specific place and time. However, quantum mechanics suggests that particles can exist in a superposition of states and can become entangled, meaning the state of one particle is linked to the state of another, regardless of distance. This non-locality challenges our everyday understanding of reality, where objects and events are typically confined to specific locations in space and time. If consciousness is indeed a quantum phenomenon, it would mean that the mind may not be confined to the physical brain, but could exist in a more holistic, non-local form, allowing for a deeper connection between consciousness and the universe. On the other hand, the traditional view of consciousness is grounded in the physicalist or materialist perspective, which holds that consciousness is strictly a product of physical processes in the brain. According to this view, the mind is an emergent property of the brain's neural networks, which process information and give rise to thought, perception, and self-awareness. Proponents of this model argue that the brain's complex or structure composed of billions of neurons, trillions of synaptic connections can explain all aspects of consciousness through physical interactions and chemical signals. According to the materialist view, consciousness is entirely dependent on the physical brain. When the brain ceases to function, so too does the experience of consciousness. This physicalist explanation of consciousness is often associated with reductionism, the idea that complex phenomena can be fully understood by breaking them down into their simplest components. From this perspective, there is no need for any non-physical or mysterious forces at play. Consciousness is simply a byproduct of the brain's biochemical processing, governed by well-understood principles of neurobiology and electrochemical activity. For example, patterns of electrical firing between neurons lead to the processing of sensory input, emotional responses, and higher cognitive functions like decision-making and planning. Cognitive neuroscience has made significant strides in mapping the regions of the brain responsible for different aspects of consciousness, providing a physicalist framework for understanding the mind. However, the quantum consciousness hypothesis challenges this reductionist view by suggesting that consciousness might not be reducible to the mere firing of neurons or chemical reactions. Rather, it might emerge from more fundamental processes at the quantum level, where the rules of physics are far less deterministic and far more probabilistic. For example, quantum superposition allows particles to exist in multiple states simultaneously, and entanglement means that distant particles can influence each other instantaneously. If these quantum processes are happening in the brain's microtubules, it would imply that consciousness is not merely a classical, local phenomenon, but a more fluid and entangled process that transcends the physical brain. This view opens up the possibility that consciousness might not be local at all, suggesting that it could be a non-physical aspect of reality that is not confined to the brain or the body. The implications of quantum consciousness theories are profound, as they suggest that our experience of being conscious could be far more complex and interconnected with the fabric of the universe than we have ever imagined. If consciousness arises from quantum processes, it might mean that we are not just observers of the universe, but also active participants in shaping its structure at a quantum level. This could provide new insights into phenomena like intuition, precognition, and non-local consciousness, where individuals seem to perceive or experience information beyond the limits of space and time. In conclusion, the debate between quantum consciousness and physicalism highlights the profound mysteries surrounding the nature of the mind. While the physicalist model sees consciousness as an emergent property of the brain's complex interactions, quantum theories suggest that the mind may be a more fundamental phenomenon rooted in the quantum fabric of reality itself. If consciousness is indeed a quantum process, it could redefine not just how we understand the mind, but also how we view our relationship to the universe. The question of whether consciousness is a physical or non-physical phenomenon remains one of the most intriguing and challenging questions in both philosophy and physics, and its resolution could shape our understanding of reality itself. Could we escape into a new reality? The idea of consciousness escaping the known universe through black holes taps into a fascinating and speculative intersection of physics and philosophy. Black holes, long considered the most mysterious and destructive objects in the cosmos, have been theorized to hold more than just physical matter. They may be gateways to alternate realities or even new dimensions of existence. Could consciousness, in its most fundamental form, transcend the confines of our universe by passing through a black hole? This speculative question invites us to consider whether black holes could act as a kind of bridge to another reality, one that exists beyond the reach of our known laws of physics. The idea of consciousness escaping the universe through a black hole is rooted in several speculative ideas from quantum mechanics and cosmology. One key concept is that of the multiverse, the theory that our universe is just one of many, each with its own laws of physics, constants, and dimension. According to certain models, black holes might not only mark the end of a star's life, but also serve as portals to other universes. If black holes can create wormholes, hypothetical shortcuts through space-time, it's possible that they could provide access to new realities entirely different from our own. The idea is that as an individual or consciousness crosses the event horizon of a black hole, their physical body might be torn apart by immense tidal force. But what if consciousness itself, not bound by the physical body, could somehow pass through the event horizon and emerge in a completely different region of reality? This might suggest that consciousness is not entirely dependent on matter or space-time, but is instead a more fundamental phenomenon capable of transcending the boundaries of the universe as we know it. One theoretical model that supports this idea is the holographic principle, which suggests that the three-dimensional universe we experience might actually be a projection of information encoded on a two-dimensional surface, such as the event horizon of a black hole. In this framework, the information about the physical universe is stored on the black hole's boundary, and consciousness, if it is encoded in information, might similarly transcend the constraints of physical space, just as the universe may be a holographic projection from a more fundamental reality. Consciousness might be able to escape the known universe and enter a different, higher dimensional reality. Additionally, the concept of quantum entanglement suggests that particles in different locations can become linked, even across vast distances, suggesting that space itself may be less isolated and more interconnected than we perceive. If consciousness operates at the quantum level, it might also be able to leverage this non-locality, allowing it to escape from the confines of the physical universe through a black hole, entering an entirely new quantum reality. This possibility raises questions about the nature of the self. Could consciousness be detached from the physical universe and reinsert itself into a new, independent existence? A further intriguing idea involves the simulated universe hypothesis, which proposes that our reality might be a simulation created by a more advanced civilization. In this speculative scenario, black holes could represent the boundary of the simulation, like a reset button or a gateway to a more fundamental or alternate simulation. Consciousness, freed from the constraints of the simulated universe, might then escape into another simulation or reality, stepping out of the bounds of the current system altogether. This idea is grounded in philosophical discussions about the nature of existence and the possibility that our universe might not be the only one. Just as we create virtual worlds in computers, perhaps our reality is the creation of a higher intelligence, and black holes could represent a means of exit from this construct. In some interpretations, black holes might also be seen as a cosmic recycling system. The matter and energy that falls into a black hole are theorized to be absorbed and, in a sense, transformed. Could this mechanism extend to consciousness? Might the energy or information of the conscious mind upon crossing the event horizon be repurposed or reborn into a different form or reality? This speculative idea draws upon Eastern philosophies, where consciousness is not viewed as a static entity but as an ever-flowing force, constantly changing and evolving. A black hole could act as a transition point, a cosmic stage where consciousness is recycled, continuing its existence in an entirely new framework of space and time. Despite these intriguing speculative ideas, significant obstacles remain in understanding how consciousness could escape a black hole. The extreme environment inside a black hole is thought to be so destructive that anything, including information, is lost beyond the event horizon. The idea that consciousness could survive such an ordeal challenges our understanding of both quantum physics and the nature of self. Without a unified theory of quantum gravity, which would reconcile the effects of general relativity with quantum mechanics, it is impossible to say with certainty whether the conditions near a black hole could support such extraordinary phenomena. In conclusion, the notion of consciousness escaping through a black hole and entering another reality is a speculative yet profoundly fascinating idea that challenges our understanding of space, time, and the mind. Whether consciousness can transcend the boundaries of our universe, pass through a black hole, and emerge in a different realm of existence remains unknown. However, the speculation raises important questions about the fundamental nature of consciousness and its connection to the universe itself. If consciousness is not solely a product of the physical brain, but something more fundamental, then Black holes could represent not just cosmic boundaries, but gateways to new realms' realities beyond the reach of our current understanding. Is the universe a simulation? The concept that black holes could be part of a simulated reality is one of the most thought-provoking and speculative ideas in both philosophy and theoretical physics. The simulation hypothesis proposed by philosopher Nick Bostrom suggests that advanced civilizations might have the capability to create highly sophisticated simulations that are indistinguishable from reality. In this context, black holes could serve as key features or boundaries within a simulated universe, potentially acting as the edges of the simulation, where the fabric of reality itself breaks down. This notion raises deep philosophical questions about existence, consciousness, and the nature of the universe we live in. The idea that we might be living in a simulation is rooted in the premise that a sufficiently advanced civilization could construct computational models of entire universes, simulating everything from fundamental particles to the cosmic structure. According to the hypothesis, our perceived reality, with all its laws of physics and complex structures, could simply be a program running on a highly advanced computer system. This concept gains support from the remarkable advances in computational power and virtual reality technology, where simulations can already mimic reality in increasingly convincing ways. If the computing power of future civilizations reaches a sufficient threshold, they might be able to create simulations that are indistinguishable from actual reality. Black holes, in this speculative framework, could represent more than just cosmic objects. They could be artificial constructs or gateways within the simulation. Some theorists argue that the event horizon of a black hole might act as a boundary between different layers of the simulation, or even between the simulated universe and the real world beyond. This idea draws on the notion that simulations, like any virtual world, would have limitations or boundaries, places where the simulation encounters its limits, or where exotic events, like black holes, might occur. Rather than being sites of destruction and mystery, black holes in a simulation could serve as mechanisms to reset or refresh the system, where matter and information are efficiently recycled, allowing for the maintenance of the simulation's internal consistency. This theory is further supported by the holographic principle, which proposes that the information contained within a three-dimensional region of space could be encoded on its two-dimensional surface. If black holes are part of a larger simulated system, this principle could suggest that the information within a black hole, everything that falls in, might not be lost, but instead encoded on the event horizon, much like the way data is stored on the surface of a hard drive or disk. This aligns with the idea that black holes could be data processing nodes within the simulation, acting as conduits for information transfer and storage. In this way, black holes might be fundamental to the functionality of the simulated reality, serving as hubs where information is gathered, compressed, or even deleted. The idea that black holes could be part of a simulated universe raises profound questions about the nature of reality. If the universe is a simulation, then everything we experience, from the distant stars to our own thoughts, could be the result of complex algorithms running on some cosmic computer. This would mean that the fundamental laws of physics, including general relativity and quantum mechanics, are simply rules written into the simulation, not laws governing an independent, physical reality. In this context, black holes would no longer be seen as ultimate destroyers of matter and information, but as calibrated events designed to maintain the integrity of the simulation. They could be mechanisms used by the simulators to manage and control the computational process, ensuring that the simulated universe continues to function properly. From a philosophical standpoint, this theory challenges the very nature of consciousness and existence. If we are living in a simulation, the reality we perceive might be no more real than a video game or virtual reality environment. A subjective experience of life, emotions, and thought could be the result of simulated processes running in a computer system. And our sense of free will might be illusory, a byproduct of the simulation's algorithm. However, this realization does not necessarily diminish the value experience, as the simulation hypothesis implies that the conscious experience is real in the sense that we perceive and interact with the world around us, regardless of whether that world is constructed artificially or not. Another intriguing angle is the ethical implications of such a simulation. If black holes and other cosmic anomalies are part of a simulated reality, then the question arises, who is in control of the simulation? Could the creators of the simulation be aware of our existence and potentially have the power to influence or even alter the simulation? In this scenario, black holes could serve as intervention points where the simulators might manipulate the course of events or allow for certain emergent behaviors. Alternatively, the simulated universe might be fully autonomous, with black holes and other phenomena acting as natural phenomena within the programmed parameters. Despite its speculative nature, the idea that black holes could be part of a simulated reality forces us to confront fundamental questions about the nature of consciousness and reality itself. It suggests that the universe we observe might not be as real as we think, but rather a complex simulation, and the black holes traditionally seen as points of ultimate destruction might actually be designed to manage the flow of information within this vast computational system. While this concept is purely speculative and lacks empirical evidence, it opens the door to further exploration of the relationship between consciousness and reality, and could one day lead to a more profound understanding of both the physical universe and the nature of our own mind. What black holes teach us about the universe? Black holes have long been one of the most profound and enigmatic phenomena in the universe. They push the boundaries of our understanding of space, time, and physics to the breaking point. Their mysterious nature forces us to reconsider some of the most fundamental principles that govern reality. As we attempt to understand black holes, we are compelled to confront the limitations of our current theories, and in doing so, we are often led to profound insights that challenge our basic assumptions about the cosmos. First and foremost, black holes force us to reconsider the nature of space-time itself. According to general relativity, black holes represent regions where the fabric of space and time are warped to extremes. The event horizon, the point of no return surrounding a black hole, marks the boundary where space and time lose their traditional meaning. As matter approaches a black hole, time appears to slow down relative to an outside observer, and space itself is stretched and distorted by the black hole's immense gravity. This phenomenon challenges our classical understanding of time as a linear and steady flow. Inside the event horizon, the usual distinctions between time and space appear to break down. Time could be experienced as a spatial dimension, and space could become an inescapable feature of the future. Black holes, therefore, are not just points of destruction but also test cases for the limits of space-time, offering a glimpse into a reality that is far more fluid and dynamic than we typically perceive. Furthermore, black holes compel us to question the nature of information and entropy in the universe. According to general relativity, when matter or light crosses the event horizon, it is lost to the universe, seemingly disappearing into the singularity at the center of the black hole. However, quantum mechanics dictates that information cannot be destroyed. This principle of unitarity is central to the theory. The tension between these two ideas, the classical idea of information loss and the quantum principle of information preservation, has given rise to the black hole information paradox, one of the most significant unresolved problems in theoretical physics. Could it be that black holes do not destroy information, but rather encode it in some form, such as on the event horizon? The speculative holographic principle suggests that the information about everything that falls into a black hole is not lost, but rather preserved on its two-dimensional surface, potentially leading to a rethinking of how information is stored and processed in the universe. Black holes, in this sense, challenge our understanding of entropy, the arrow of time, and the fundamental laws of quantum mechanics. In addition to these insights, black holes also force us to re-examine the limits of knowledge and observation in physics. The event horizon represents a boundary that marks the limit of the observable universe. Beyond it, we cannot observe or measure anything. This boundary of knowledge raises important philosophical questions about the nature of reality and the role of the observer in shaping it. If we cannot observe what lies beyond the event horizon, does it mean that it does not exist? Or does it exist in a state that is fundamentally inaccessible to us? This uncertainty challenges our assumptions about the nature of the universe and our ability to fully comprehend it. In this way, black holes become metaphors for the unknown, reminding us of the limits of human understanding and the vastness of the mysteries that remain. Moreover, black holes also force us to reconsider the interconnectedness of the universe. The study of wormholes, which are theorized to be linked to black holes, suggests that space-time might not be as isolated as we once thought. Wormholes are hypothetical tunnels through space-time that could connect distant regions of the universe or even different universes entirely. While wormholes remain speculative and have not been observed, their theoretical existence challenges our classical notion of space as a vast, isolated expanse. Instead, it opens the possibility of a more connected universe, where different regions of space-time could be linked in ways that we do not yet fully understand. Black holes, through their potential connection to wormholes and their role in shaping the fabric of space-time, invite us to think of the universe as a network of interconnected phenomena, rather than a collection of isolated regions. In addition to these physical insights, black holes also challenge our perceptions of cosmic evolution. Traditionally, black holes have been seen as the ultimate endpoints of stars, places where matter is crushed to infinite density. However, recent theories, such as the baby universe hypothesis, suggest that black holes might also be the starting points for new universes. In this view, the singularity at the center of a black hole could represent a cosmic rebirth, a new region of space-time where the laws of physics could evolve in entirely new ways. This idea pushes us to reconsider the nature of cosmic cycles and the possibility that our universe could be part of an infinite sequence of births and deaths, with black holes serving as the gateways between them. Ultimately, black holes force us to confront the limits of our understanding and to expand our ideas about space, time, and reality. They challenge the fundamental principles of physics and philosophy, pushing us to reconsider our assumptions about the nature of the universe. Through their mysterious, powerful presence, black holes have become windows into a deeper understanding of the cosmos, revealing that the universe is far more complex and mysterious than we can yet comprehend. Whether they are seen as destructive forces or as gateways to new realities, black holes continue to inspire awe and wonder, reminding us of the vastness of the unknown and the infinite possibilities that lie beyond the limits of our current knowledge. Time travel as a metaphor, black holes have long captured the imagination of scientists and storytellers alike, not just as real cosmic objects, but as profound metaphors for some of humanity's deepest existential questions. While time travel as a literal concept remains firmly within the realm of speculative physics and science fiction, black holes have become a powerful metaphor for the ultimate journey into the unknown, a passage to a realm where space, time, and reality itself are transformed in unimaginable ways. In this sense, black holes are not only physical phenomena but are emblematic of our human quest to transcend the boundaries of ordinary existence and explore the mysteries that lie beyond our comprehension. At the heart of this metaphor is the event horizon, the boundary surrounding a black hole beyond which nothing, not even light, can escape. The event horizon acts as a point of no return, a literal boundary that marks the transition from the known universe to a realm of chaos and uncertainty. In many ways, this mirrors the concept of time travel, which involves venturing beyond the constraints of present reality into an unknown future or past. Just as the event horizon represents a threshold that leads to unobservable and potentially dangerous territory, time travel represents a crossing from the familiar into the unfamiliar, where the very fabric of reality might be stretched or distorted. In popular culture, black holes are often used as metaphors for human exploration. Whether it's venturing into the unknown corners of the universe or confronting the mysteries of the self, just as time travel in science fiction often involves characters stepping into a future or past that they cannot control, crossing the event horizon symbolizes the loss of agency. Once inside a black hole, one can no longer return to the familiar world outside. Time travel, in this metaphorical sense, is not just about the possibility of changing history or seeing the future, but about confronting the irreversibility of the journey. Like the journey through a black hole, time travel forces one to confront the inevitable consequences of their action, choices, and perceptions. The black hole metaphor for time travel also speaks to the ineffable nature of the journey. While black holes are scientifically understood as regions of space where the laws of physics break down, they remain fundamentally mysterious and inaccessible to human experience. Similarly, time travel in theory is deeply speculative, full of paradoxes and complexities that make it difficult to envision practically. Just as we cannot truly experience the interior of a black hole without being torn apart by spaghettification or crushed by immense gravitational forces, we cannot fully understand what it would mean to travel through time. Because such a journey transcends the limits of our understanding of space-time and causality. In this sense, black holes represent the ultimate unknown, a boundary that separates what we know from what lies beyond. In philosophical terms, the idea of time travel as a metaphor invokes the human desire for transcendence, the yearning to escape the constraints of ordinary life and experience something otherworldly. Time travel allows for the possibility of rewriting history, of gaining a deeper understanding of the future, or of altering the course of events to suit one's desires. Black holes, as a metaphor, reflect the way in which we constantly grapple with the passage of time, our desire to escape its linearity, and our need to understand both our origins and our fate. They are a reflection of the tension between determinism and free will, as the forces within a black hole are beyond control and beyond understanding, much like the seemingly fate-driven flow of time in our own lives. Moreover, time travel through the lens of black holes also taps into the theme of existential risk. Just as crossing the event horizon of a black hole means entering a region of space where conventional understanding of physics and reality breaks down, time travel carries with it profound risks, from the potential for paradoxes to the irreversible effects that changes to the past might have on the future. This reflects a human anxiety about pushing the boundaries of knowledge and exploring unknown territory. Just as time travelers in fiction must grapple with the ethical and philosophical implications of altering the course of history, those who attempt to understand or manipulate black holes must confront the very real risks of disrupting the natural order of the universe, where we cannot predict or control the outcomes. Despite these risks, black holes also represent opportunity, the possibility of transformation. If time travel through a black hole could ever become reality, it would open up new frontiers for human exploration, allowing us to journey not just through space, but through time itself. Similarly, black holes, though seemingly destructive, offer insight into the fundamental nature of the cosmos. They could provide a window into the origins of the universe, the nature of gravity, and the mysteries of quantum mechanics. In this way, black holes serve as both a symbol of destruction and a potential gateway to understanding the most profound truths about the universe and our place within it. In conclusion, black holes serve as the perfect metaphor for time travel, reflecting our deepest desires and fears about the nature of existence, the flow of time, and the unknown. They represent the ultimate boundary between what we know and what we cannot fathom, challenging our understanding of reality and forcing us to confront the limits of human knowledge. Through black holes, we are reminded that time travel is not just a journey through the past or future, but a journey into the heart of the unknown, a realm where even the laws of physics break down and where new possibilities for the universe and consciousness may lie waiting. The final mystery, what lies beyond? As we stand on the edge of understanding, black holes remain one of the greatest mysteries in the universe. While they are often viewed as extreme objects in physics where the very fabric of space and time is distorted, the true significance of black holes may go beyond the scientific. Their enigmatic nature might speak to something deeper, our place in the cosmos and our relationship to the unknown. The mystery of what lies beyond the event horizon is not just about understanding the laws of gravity, quantum mechanics, or relativity. It is also a reflection of humanity's existential quest to find meaning in an overwhelmingly vast and incomprehensible universe. At the heart of the black hole, mystery lies a paradox. We can observe their effect, their presence and their role in the cosmic landscape, but we can never know for certain what happens beyond the event horizon. This boundary between the known and the unknown mirrors the very limits of human knowledge. The more we learn about the universe, the more we realize that answers often lead to new questions. Just as black holes are invisible in the traditional sense, there are aspects of reality that remain hidden from our understanding, waiting to be explored by future generations. This paradox, the tension between knowing and not knowing, is not only a challenge to science, but also to our sense of self and purpose within the vast, indifferent cosmos. The fact that black holes are regions where even light cannot escape highlights our fragility in the face of the universe's complexity. As human beings, we are constrained by our finite perspectives, bound by the limits of time and space. Yet, black holes represent the ultimate unknown places where time itself may behave differently, where the laws of physics as we know them may not apply. In this sense, they challenge us to reconsider not just what the universe is, but what it means for us to exist within it. Perhaps in our search for answers about black holes, we are also searching for answers about ourselves. Who are we in relation to this vast and mysterious cosmos? What is our role in a universe that contains such wonders and dangers? Moreover, black holes, in their role as cosmic singularities, might serve as metaphors for the limits of human experience. As we look to the farthest reaches of the universe, we confront the terrifying yet awe-inspiring idea that there may be boundaries to knowledge and understanding, places where our concepts of space, time, and existence no longer make sense. The singularity at the heart of a black hole represents the ultimate boundary, a point where physics breaks down, where all known laws collapse into a state of infinity. This may be a reminder that there are mysteries in the universe that, for all our intellectual curiosity, may remain forever beyond our grasp. But this realization need not be disheartening. In fact, the very existence of such mysteries can be a source of wonder and inspiration. The mystery of black holes challenges us to look beyond the confines of what we know and contemplate the unknown. It encourages us to accept that not everything has a neat, definable answer, and that the journey of discovery is often just as important as the answers we seek. The unknown may not only be a scientific challenge, but a philosophical one, reminding us of our place in the cosmos and the limitations of our human perspective. In closing, black holes remind us of the unfathomable scale of the universe and our position within it. They force us to confront the fragility of our understanding and the awe-inspiring complexity of reality. Perhaps the true mystery of black holes is not just their physical properties, but the way they reflect our own search for meaning in the vast and incomprehensible universe. As we look beyond the event horizon, we are not only looking at the edge of space and time, but also into the heart of our own existence, and that, in itself, is a journey worth embarking upon.